So we're going to talk about axial members and what kinds of effects thermal changes in temperature would have on these members. So again, we're talking about axial members. So we're focusing on the effects in the longitudinal direction of a member. Here I have an example of two unrestrained columns in the sense that they're fixed at one end. Here we have a pin, here we have a fixed support. At the other end, they're free to displace longitudinally. On this side, we have a doubly restrained column where it's fixed at the left end, it's fixed at the right end. And this is an indeterminate system, and we'll see that thermal effects have a much more profound effect on stresses here than they do for the unrestrained condition. So the first thing that we need to figure out is if we're subjected to a change in temperature. So it's just like an external load, but it's not applied at a specific location. Let's say that both of these were subjected to some change in temperature. And we could say that's equal to some final temperature T2 minus an initial temperature T1. So both of these, if it's a positive delta T, that means that the temperature has increased. If it's a negative delta T, that means that the temperature has decreased. But so either of these columns right here, if they were subjected to a temperature increase or decrease, they would be free to expand or contract in the longitudinal direction. And so what would happen for this top, that's a simply supported column where we have a pin and a roller. The pin would prevent translation longitudinally, but the roller would allow it. And so we would get some change in length here. And I'll just call that delta T. It means this column is going to get longer. And for the column down below, it's the same basic system in the sense that the left is fixed, the right side is free, and so this will do the same thing. This will also deflect that same amount, delta T. And one question that we have is how do we calculate delta T based off this change in temperature? And again, this is capital delta T, so I apologize. This is lowercase delta, meaning a change in length, uppercase delta meaning, for delta T, meaning the change in temperature. And what we find and what the book tells you is that the change in length of an unrestrained axial member due to a change in temperature is equal to alpha times delta T times L. Now, we already know what delta T is. That's the change in temperature. Positive would mean an increase, negative would mean a decrease. L is simply the original length of the member. And alpha is a new concept or a new material property. It's called the coefficient of thermal expansion. And so alpha is called the coefficient of thermal expansion. And that's a material property. You would need to look that up in the back of your book. Commonly, the units on this are going to be 1 divided by whatever coordinate system's temperature measurement you're in. So that could be 1 divided by degrees Fahrenheit, or it would be 1 divided by degrees Celsius. You could do Rankine and Kelvin as well too, but here we're talking about change in temperature, so it doesn't really make a difference where we're talking about Fahrenheit or Rankine or Celsius or Kelvin. The units work themselves out where this is 1 divided by temperature. This is temperature, so those cancel out. L is in units of distance, and so you get a distance as the result for this equation. Now, you can also calculate the thermal strain, and because we've already defined strain, let's say sigma T for thermal strain, our definition of normal strain in the longitudinal direction is equal to the change in length divided by the original length. So here if we said the strain is equal to the change in length delta T divided by the original length L, we can actually expand out this because we have the equation up above, alpha times delta T times L in the numerator, L in the denominator. We can simply cancel out the L's here, and the thermal strain is simply equal to alpha times delta T. That's if it was asking for strain. Sometimes it'll ask for the change in length due to the change in temperature. It just depends on the call of the question. So for an unrestrained column like this, the calculation is very simple. All that you would be doing here is looking up in the back of your book what alpha is for the material, calculating your change in temperature. And again, the sign convention works here because alpha is always going to be positive, L is always going to be positive. So the only thing that affects whether you're calculating a reduction in length or an expansion in length is delta T, and an increase in temperature would cause a positive delta T, which makes sense. When we heat things up, they tend to expand. And then L is just the original length, so a pretty straightforward calculation. And for determinate structures, it's relatively straightforward. One more thing before we get to the indeterminate structures that I want to talk about is that in addition to calculating the change in length, you might be interested in calculating the change in width. So here I'm just going to call the depth of this beam lowercase d. And so if, let's say, I wanted to calculate the change in width, so I'll call that delta T sub d, whereas this would be delta T sub L. The change due to temperature of the length, here the change due to temperature of the depth of this member. It's basically the same equation, but instead of using the original length, we're just going to use the original depth of the member. So that'll be alpha times delta T times d, where d is just the original width of the member. So thermal effects have a significant difference as compared to, say, force-based effects, because here the thermal strain in the longitudinal direction is exactly the same as the thermal strain in the transverse direction. Whereas if we had a column that was subjected to a compressive force, we'd have a negative longitudinal strain, and then we'd have a positive transverse strain, and that transverse strain would have a lower magnitude than the longitudinal strain because of Poissons ratio. So I think that's an important point, so let's talk about that just a little bit. So one more time, just to make it as clear as possible, if we have a column like this, let's say pin and roller, and I have some change in temperature, delta T, that's applied to this column. And let's say that I want to calculate the change in length, but I also want to calculate the change in the depth, delta T sub d. The strain in this direction is the same as the strain in this longitudinal direction. And so the strain, it doesn't matter which way we're looking, the strain will be constant. The strain due to the change in temperature equals alpha times delta T. Alpha we look up in the back of the book, delta T, for this problem at least we're assuming that it's given to us. So this thermal strain applies whether we're looking longitudinally or we're looking transversely. So now if I want to apply this strain to calculate a change in length or a change in width, I would simply, to calculate the change in length, it would be equal to the thermal strain times the original length. If I wanted to calculate the change due to temperature of the width, it would be that same thermal strain times d naught, where d naught is just simply the original transverse direction, and L naught is simply the original longitudinal direction length. So that's thermal strains, but what if we, instead of having a thermal load, let's say that instead I'll put a tensile load onto this member here. So here, just some external load P. This column is subject to pure tension, and our question remains the same. It's asking us what is the change in length due to that applied load, so delta P sub D, what's the change in the width due to this applied load, and here, what is the change due to the applied load of the length. Now I've drawn both of these changes in the length and in the width in the positive sense. We know from experience and from what we learned about Poissons Ratio that it's going to get longer in the longitudinal direction because it's in tension, but due to Poissons Ratio, it's actually going to get more narrow. I've drawn these both positive. If we get a negative value, that just means it's going to be getting smaller. Okay, so it's the same idea. We need to calculate, well, there's a couple different ways that we can do this. We could try to calculate the normal strain due to the load in the longitudinal direction, but we have a shortcut for calculating the change in length. So the change in length due to the applied load in the longitudinal direction. Here we have a constant cross-sectional area. We've got a constant load, internal normal force, the entire length. So I can say NL over AE. The internal normal force in this case is just going to be equal to P. If we did a quick free body diagram in the section cut, L is just equal to L, A and E, we're assuming that those are given for this problem. So the change in length in the longitudinal direction, here it's going to be positive if P is positive, and we can calculate it pretty easily. The change in length due to the applied force, or sorry, the change in width due to the applied force is a little bit trickier. We need to calculate the normal strain in that transverse direction due to that applied load. And then we need to multiply it by the original width. This is where it gets a little bit tricky. This is where Poissons Ratio comes into play. Here, to calculate the transverse strain, we need to use Poissons Ratio. That said Poissons Ratio is equal to the transverse strain divided by the longitudinal strain, and there's a negative symbol out in front of this. So if I rearrange this, I get that the transverse strain is equal to minus Poissons Ratio times the longitudinal strain. Longitudinal strain we can calculate just from this equation here. This is the change in length. We can divide it by the original length, and we simply would get the longitudinal strain is equal to N over AE, and we know that N is just equal to P. All right, and so I can plug that into here as well too. This is going to be equal to N over AE. And so I could plug this entire equation here into the transverse strain in this equation, and I get that the change in length, change in width due to the applied load is equal to minus Poissons Ratio times N over AE times D naught. So a very different process to calculate the transverse effects if you have a load-based effect compared to the transverse strain or transverse change in width if you're talking about a thermal effect. The thermal effects are much easier to deal with because it's the same strain transversely as it is longitudinally. Now this gets into another issue where we're not always just going to have a change in temperature or just an axial load being applied. It's possible that we could have both acting at the same time. And so if that's the case, you need to superimpose the effects of these, but you need to keep them separate. You need to do bookkeeping and keep each of them separate because the key to Poissons Ratio is that it relates the transverse strain to the longitudinal strain, but these strains here are only the strains due to the load effects. So I'm going to put a subscript P on each of these, or on the longitudinal, it only cares about how much longitudinal strain is caused by the external load. You wouldn't calculate the longitudinal strain here, including any thermal effects. This is only going to be the N over AE type component, only the longitudinal strain due to the externally applied loads. So let's work on bookkeeping here. Same type of problem, but now let's apply both types of loads. So here I have delta T, some change in temperature applied, plus I have some externally applied axial load, putting it into tension. And here I'm going to be interested in finding the overall change in length and the overall change in width. Here we have our original width or depth, which is d naught. Here we have an original length, which is L naught. And so our question is, how much longer is this member going to get, and how much deeper or how much wider is it going to get? And it's really just a superposition of the thermal effects and the force-based effects. So here, let's talk about the length first, because that's the easier of the two. So here, the change in length is equal to the change in length due to the applied load P, so delta PL, plus delta TL, the change in length due to the applied load P, and the change in length due to the change in temperature T, or delta T. And we know the equations for each of these is pretty straightforward. For an axial member subjected to a constant internal normal force and a constant cross-sectional area, this is simply NL over AE. In this case, the internal normal force is just going to be equal to P, and we can assume that we have A and E. And the change in length due to the change in temperature is the equation we talked about previously, alpha times delta T times L. And pretty much all those we can assume that we have. Again, material properties, cross-sectional area, material properties, change in temperature. And we could calculate the change in length pretty easily. Now the trickier part, so here's the longitudinal direction. The trickier part is going to be the transverse direction, excuse me. So the transverse direction, we'll call that delta sub D, the change in the transverse direction, is still going to be equal to some change in width due to the applied force. So delta P sub D, the change in depth due to the applied force, plus the change in depth due to the thermal effects. And this is where keeping the two of them separate is really critical. So here, the change in depth, the change in width due to the externally applied force, that's due to Poissons Ratio. That's all of this work that we just did right here. But the critical part, just like I mentioned before, is that Poissons Ratio is only relating, and I can put a P here as well too, it's only relating the strains caused by the externally applied load P. This calculation here ignores completely any thermal effects going on. So when you calculate the longitudinal strain, you would not include both the change in length due to the force and the change in length due to the temperature. You would only include the change in length due to the force. And that change in length due to the force, if we have a simple section like this, is NL over AE. Then to get the strain, it would be NL over AE divided by L, which is the same thing as just N over AE. And so this equation here applies if you have a constant cross-sectional area and a constant internal normal force. In this example we do, but that's not always going to be the case. So let me then just bring in this evaluation we did a second ago. This will be equal to minus Poissons ratio times the internal normal force times d naught divided by AE. And then plus, now for the change in width due to the thermal effects, that's pretty easy. The thermal strain is the same transversely as it is longitudinally. So then to calculate the change in width from the thermal strain, we just multiply by the original width. So this is the only component that I need to bring over there. And we get alpha times delta T times d naught. So the most common mistake is right here. Students will often put delta L divided by L times Poissons ratio, minus Poissons ratio times d naught. And that includes the thermal strains in Poissons ratio, which is a big no-no. So here you'll notice that if we have tension and we have a positive change in temperature, both of them will be additive in the longitudinal direction. Both will be making this column longer. Whereas down here, if we have tension in the longitudinal direction, it's going to be causing contraction transversely, whereas a positive change in temperature is causing it to expand transversely. So here, they work against each other. You're always going to find that either in the longitudinal direction or in the transverse direction, the force effects and the thermal effects, in one of those cases will have to be opposing, and in the other case, they'll have to be additive. All right, so now let's transition and talk about an indeterminate axial member that's subjected to thermal effects. So let's talk about an indeterminate column. And so all that I'm going to do to change this from determinate to indeterminate is add a fixed support on the right-hand side as well. And here it's indeterminate, we're talking about thermal strain, so I'm going to apply some change in temperature to the system. And so with this setup right here, the column can't actually change its length. It's fixed on the left, it's fixed on the right. So even though I'll apply a change in temperature and it wants to elongate, these fixed supports prevent it. And I think it's helpful to think about the force and flexibility method here, because that kind of breaks up or shows you how these thermal effects will end up inducing an internal force here, whereas when it was unrestrained, there'd be no internal force induced by a thermal change in temperature. So let's just say this is a superposition of two different situations. This is like the force flexibility method. I'm going to take away the support on the right-hand side, and let's go ahead and see what happens. So if I take away the support on the right-hand side, based off the force and flexibility method, I need to then, that's what we call our primary system. And now I'm going to take this primary system and I'm going to apply two different load cases to it. Now the first load case is simply just the external forces. And here we don't have any actual forces applied. This change in temperature, that was what we would consider the loading, or the external loading here, external forces. So I have some change in temperature, and based off that loading, I need to keep track of the deformations at the location where I took away the support. So this is just a determinate structure, so calculating the change in length where I took away the support, we'll just call this delta due to T for temperature. This column is going to get longer, and I can easily calculate what that's equal to It's just alpha times delta t times L. Now, we know that adding these two systems together, we have to have zero deflection at the right-hand side, because that's the boundary condition here. This has a fixed support, which means that there can't be any deflection over there at all. So here, I'm going to put the support reaction that's missing here back onto this system. I'm going to draw it pretending like it's an internal force, and so I'll draw it in tension, and I'll just call this R sub B. I should probably label these points, A and B, A and B, A and B. And again, the direction here doesn't really matter, the assumed direction. I'm treating it like an internal normal force, showing it in tension, just to try to not confuse things. But if I get a negative value, it just means it's going to be pointed in the other direction. And I think that's the case. It's going to be pointed in the other direction, which means we just get a negative value. So here, I still need to keep track of the deflection due to this new redundant support reaction. And so I'm going to call this the change in length due to this reaction, delta R. And now I drew the deflection following the same sign convention as my assumed force here. Positive is elongation or tension. Okay, so we know that both of these changes in lengths added together has to equal 0, because this point B doesn't get any further, doesn't move at all to the right or to the left. And so kind of combining these two back down together, I know that the total deflection at B equals 0, and then I can also write the total deflection of B as equal to delta T plus delta R. So this is the change in position of B due to the thermal effects plus the change in location of B due to the reaction R. We already have the equation for delta T. That's alpha delta TL. The equation to calculate the change in length of point B due to this applied load RB. This is just a prismatic column subjected to a constant internal normal force. And so the equation here will be NL over AE. In this case, the internal normal force, if I were to make a section cut here, do a free body diagram to calculate what the internal normal force would be, it's just going to be equal to RB. So the internal normal force is just going to be equal to RB. So I can take each of these equations for delta T and for delta R, and I can plug them in right here, and I get that 0 equals alpha delta T L plus RB L over AE. In this case, we're looking for the reaction, the force that's induced by this temperature. And so I can simply rearrange this. I get that RB equals minus alpha delta TL times AE over L. And so I can cancel out the L's here, and I get this equal to minus alpha delta T times AE. So these two terms right here, alpha and delta T, alpha would be in units of 1 divided by degrees, delta T is in degrees, those cancel out. A is going to be in units of, let's say, distance squared, I'll say inches squared, and E is going to be in units of force per unit area, stress, or in other words, like example of kips per inch squared. The areas will cancel themselves out, and I'll be left with just units of force, which makes sense because we're looking for a reaction. All right, so this is one way to look at it. The change in temperature wants to make this column longer, but we know in reality the column can't get any longer, and what's counteracting that deflection due to the thermal effects is a force reaction coming back. So for an indeterminate structure, a change in temperature will induce internal forces and internal stresses. So a problem like this, you could ask a couple questions. You could say, here's a geometry and material properties, here's a change in temperature, what is the internal normal force or normal stress? Or you could ask it in a different order and you could say, well, what delta T is required to reach a specific normal force in the column? And you notice here we've increased the temperature and that induced a negative internal normal force, so compression. If I were to cool this down, if I had a negative delta T, I would have gotten tension in this member. And intuitively, that makes sense. So the other way to look at this, so this is basically the force and the flexibility method that we went through here. We used a straw man approach where we took away a support, and then we looked at two different cases. We figured out what exactly needs to, do we need to counteract that desired deflection due to the change in temperature. The other method that we could look at to deal with indeterminate structures would be the stiffness displacement method. And stiffness displacement method basically has two steps. Number one, it asks you to find the internal, well, just statics or equilibrium is the first step. All right, so in this case, the first step doesn't really tell us that much. The first step, if I were to take, I mean, there could be two section cuts, it could be one. That first step is really not going to tell us that much. All that it's going to tell us, if we made a free body diagram, in this case, I mean, all it's going to have is the internal normal force on one side and the internal normal force on the other. That's just n is equal to n. It doesn't really tell us too much, right? But most of the work gets done in the second step right here, which is compatibility. All right, so n equals n. It's still basically indeterminate. Even if I include the support reactions, n equals n doesn't really tell us anything. But here for compatibility, we know that the overall change in length of this column is equal to 0. And so another way to write that, we know that delta equals 0, but we also know that the change in length of a column is equal to the change in length due to the temperature plus the change in length due to the internal normal force or some sort of loading. And so here, this is simply equal to alpha delta T L. That's the first term, change in length due to the temperature. And this is equal to NL over AE. And this is all equal to 0. So the exact same point that we got to using the force and flexibility method, we just seem to get there a little bit more directly here. So all that I would have to do is rewrite my equation to solve for n, and I get that n is equal to minus alpha delta T times AE. I canceled out the L's. And that's the exact same endpoint that we got to before. Now the tricky part about this, potentially, is that we could double check our work. We could go back and we could calculate, well, does the change in length due to the temperature plus a change in length due to the force, does that equal 0? And so we know that longitudinally, this can't change its length. That's one way to check it. But a question might ask, well, what is the change in width of this column? And that's not going to be 0. If the thermal effects and the force-based effects cancel them out longitudinally, they're definitely not going to cancel each other out transversely. And so in this case, transversely, the temperature's, let's say, increasing. That'll make it wider. And the column's in compression, which is going to make it wider in the transverse direction as well, too. And so in that case, just looking at the width, delta D, it equals some change in the width due to the thermal effects plus some change in the width due to the force-based effects. I'll say P or N, it would be the same thing. And we had just had this up previously. The change in width due to a change in temperature is simply equal to the thermal strain alpha times delta T times the original dimension, in this case we're looking at the width, plus, and this term here is based off Poissons Ratio. Because we have a column with a constant cross-sectional area, a single prismatic piece, and the internal normal force doesn't change, this ends up being minus Poissons Ratio times N over AE. This term here is the transverse normal strain, due to the externally applied loads, due to the internal normal forces. And that gets multiplied by D naught as well. And the reasons that these two terms are going to add together, and again, this is the temperature. Let's just look at the strain part of it. This first part of the term here, this is the transverse normal strain due to the change in temperature, and this term right here is the transverse normal strain due to force-based effects. We could say N for internal normal force. Again, this one is based only on the force-based effects. This is based only on the thermal effects. And the reason that these are going to add together for this example is if we have a positive change in temperature, that means that this is going to be a positive value. The width is getting larger. But in that situation, we're also going to get a compressive internal normal force, which means we have minus Poissons Ratio times a negative value. Everything else here is positive, so negative times a negative will get a positive value for this term, and these two will actually add together.